We can now turn our attention to finding the derivatives of inverse trigonometric functions. These derivatives will prove invaluable in the study of integration later in this text. The derivatives of inverse trig functions are quite surprising in that their derivatives are actually algebraic functions. Previously, derivatives of algebraic functions have proven to be algebraic functions, and derivatives of trig functions have been shown to be trig functions. So here for the first time, we're going to see that the derivative of a function doesn't need to be the same type as the original function. The derivatives of inverse functions. I have down here on if you're on the video notes PDF file, you can click on the link and that'll take you to the proofs of where these derivatives came from. They're pretty cool to watch if you do have some time. So the derivative of the inverse sine function, and sometimes you're going to see that written as the derivative of arc sine. These mean the exact same thing. So the derivative of that is 1 over the square root of 1 minus x squared. The derivative of the inverse cosine function, and again, sometimes you'll see that written as arc cosine, they mean the same thing, is negative 1 over the square root of 1 minus x squared. And then last, the derivative of the inverse tangent function is 1 over 1 plus x squared. So let's do some examples with these. Find the derivative of the function f of x equals the tangent inverse of x squared. So we can see in this case, we're going to actually have to use the chain rule. We've got an inside function. Okay. So to find this derivative, it's the derivative of the outside function. So the derivative of the outside function is tan inverse. So tan inverse, the derivative of the inverse tangent, is 1 over 1 plus x quantity squared. And in this case, our input value is x squared. So again, remember with the chain rule, you take the derivative of the outside, evaluated at the inside. So instead of that being an x, it's whatever that inside function is. And then times the derivative of the inside function. So in this case, the derivative of the inside function is 2x. So that gives us 2x over 1 plus x to the fourth. All right, so let's look at another one. Find the derivative of g of x equals x squared times the sine inverse of x. So in this case, I've got two functions that are getting multiplied together, so I'm going to use that product property. So I have the derivative of g, so g prime of x is going to be the first function times the derivative of the second, plus the second function times the derivative of the first. Okay, so that's going to give me x squared times, so the derivative of the sine inverse function, we just learned about that, is 1 over the square root of 1 plus 1 minus x squared. Okay, plus the sine inverse of x times the derivative of x squared, which is 2x. So just to write this a little bit cleaner, we get x squared over the square root of 1 plus x squared plus 2x times the sine inverse of x. Find the derivative of z equals arc sine of the quantity 2 plus t over the quantity 2 minus t. Okay, deep breaths. So what I see here, so remember arc sine is the same thing as sine inverse. For some students, it helps to actually see that, but for others, you don't need it. But I'm just going to write it here so you can kind of see. These are mean the exact same things. They're just written in a different way. Okay, so when I look at this, I see that I'm going to have to apply the chain rule. I have an inside function, and then I have this outside function. So let's first do, we'll start applying the chain rule. So we've got the derivative of z with respect to t, because t is our variable in here. Okay, so the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. But since I'm using the chain rule, instead of an x squared, we're going to put that inside function in for that. Let's make the square root bigger. So 1 minus 2 plus t over 2 minus t squared. Okay, so again, it's the derivative of the outside function evaluated at the inside times the derivative of the inside function. So it's the derivative with respect to t of 2 plus t all over 2 minus t. Okay, so that's going to be 1 over the square root of 1 minus 2 plus t over 2 minus t quantity squared. And then at this point, I'm going to have to apply the quotient rule. Okay, so that's going to be the denominator times the derivative of the numerator, which is going to be 1, because the derivative of 2 plus t is just 1, minus the numerator times the derivative of the denominator. So the derivative of the denominator is -1. And then that's all over 2 minus t squared. So we're going to get 1 over the square root of 1 minus 2 plus t over 2 minus t quantity squared times, so this, if I were to bring this out, I'm going to get 2, well, I'll just write it out. So we'll get 2 minus t minus, and I'm subtracting this entire quantity, so don't forget that. So minus -2 minus t all over 2 minus t quantity squared. So that's going to become 1 over the square root of 1 minus 2 plus t over 2 minus t quantity squared times, okay, so I'm going to get 2 minus a -2 is 2 plus 2, so that's going to be 4, and then -t minus a -t becomes -t plus t, which is 0, all over 2 minus t quantity squared. And we can leave it just like that. Now let's look at an application that involves inverse trig functions. The position of a particle at time t is given by s of t equals the tan inverse of 1 over t for t values that are greater than or equal to 1/2. Find the velocity of the particle of time t equals 1. Okay, so remember that the velocity, so finding that velocity at 1, that's going to be finding the first derivative of the position function at 1. So let's first figure out what is the first derivative function. So what is s prime of t? Okay, so again, I'm going to have to use the chain rule because I have an inside function. So it's going to be the derivative of the outside function, which is 1 over 1 plus x squared, but instead of an x, I'm evaluating it at that inside function, so I put the inside function in. And then times the derivative of the outside function, which is 1 over t. So I'm going to write that as t to the -1, just so you can see how the power rule is going to work there. So I'm going to get 1 over 1 plus 1 over t squared times negative t to the -2, which ends up giving me 1 over 1 plus 1 over t squared, all times -1 over t squared. Now you can keep on going to simplify this further, but we don't need to actually do that because it's not asking for the derivative formula, it's asking for us to find the derivative at a specific time, at time equals 1. And at this point we can actually substitute in 1 in and get our answer. So that's going to be 1 over 1 plus 1 over 1 squared times -1 over 1 squared. So that's going to give us 1/2 times -1, which gives us -1/2. So the velocity at time t equals 1 is -1/2. And it looks like they didn't give us any units, so we will leave it just like that.